Have you ever wondered where it all began? The origins of everything we see around us, from the tiniest particles to the vast galaxies. I mean everything. The stars, the planets, even you and me. The story of our universe is a tale of epic proportions spanning billions of years. It all started with a bang, a really big one. This event, known as the Big Bang, was the moment when everything we know came into existence. We call it the Big Bang. Imagine a tiny point, smaller than an atom, containing all the energy of the universe. This point was unimaginably dense and hot. Then about 13.8 billion years ago, it exploded. This explosion wasn't like any explosion we know. It was the rapid expansion of space itself. Space itself expanded rapidly, like a balloon inflating at an incredible speed. This expansion set the stage for everything that would follow. This wasn't an explosion in space, it was the expansion of space itself. The fabric of the cosmos stretching and growing. As space expanded, it carried galaxies with it, moving them further apart. As the universe expanded and cooled, energy began to transform. The intense heat and energy started to give way to the formation of matter. This transformation led to the formation of the first particles, the building blocks of matter. These particles were the seeds of everything that would come later. These particles eventually clumped together to form the first atoms, mostly hydrogen and helium, the lightest elements in the universe. These atoms were the foundation of all matter. Can you believe it? The very atoms that make up your body were forged in the fiery furnace of the Big Bang. Every element in your body has a cosmic origin. These early atoms were spread out across the vast expanse of the universe. They drifted through the cosmos, waiting for the next chapter in their journey. Gravity, the invisible force that pulls things together, began to work its magic. This force started to shape the universe, pulling atoms closer together. Over millions of years, gravity pulled these atoms closer, forming giant clouds of gas and dust. These clouds were the nurseries of the cosmos. These clouds, called nebulae, became the birthplaces of stars and planets. Within these nebulae, new stars ignited, and planets began to form, continuing the grand story of the universe. One of these giant clouds of gas and dust, called the solar nebula, would eventually give birth to our very own solar system. This vast swirling cloud was a chaotic mix of elements, a cosmic soup that held the potential to create planets, moons, and even life itself. Imagine the enormity of this cloud, stretching across light years, with countless particles dancing in a gravitational ballet. This swirling cloud wasn't just sitting still, though. Like a figure skater pulling in their arms, the solar nebula began to spin faster as it contracted under its own gravity. The more it spun, the more it flattened, creating a disc-like structure. This increase in rotation was crucial, as it set the stage for the formation of the solar system's intricate architecture. As it spun, the cloud flattened into a disc, with most of the material concentrated at the center. This central concentration would eventually become the Sun, the heart of our solar system. The outer regions of the disk, meanwhile, were teeming with activity as particles began to interact in complex ways. Within this spinning disk, particles of dust and ice collided with each other. These collisions were not random. They were governed by the laws of physics, which dictated how particles would stick together or bounce apart. Each collision was a tiny step in the grand process of planetary formation. Most of these collisions were minor fender benders, but some were more like cosmic smash-ups. These dramatic events could shatter particles into smaller pieces or cause them to merge into larger bodies. The energy released in these collisions helped to heat the surrounding material, adding to the dynamic environment of the solar nebula. Over time, these collisions caused the particles to stick together, forming larger and larger clumps. These clumps, known as planetesimals, were the building blocks of planets. They ranged in size from tiny pebbles to massive boulders, each one a potential seed for a future world. These clumps, held together by gravity, became the seeds of planets. As they grew, they began to attract more material, increasing in size and complexity. This process of accretion was slow but relentless, gradually transforming the solar nebula into a more structured and organized system. It's amazing to think that something as grand as a planet started out as tiny specks of dust. These humble beginnings remind us of the incredible processes that shape our universe. Each speck of dust carried the potential to become part of something much larger, a testament to the power of nature's creativity. As the solar nebula continued to spin, it became a cosmic construction site, with material constantly colliding and clumping together. This ongoing activity was essential for the formation of planets, moons, and other celestial bodies. The solar nebula was a place of constant change where new structures were being built and old ones were being destroyed. The central region of the disk, where most of the mass had gathered, grew hotter and denser. This intense heat and pressure were the precursors to the birth of a star. The material in this region was undergoing a transformation, driven by the forces of gravity and nuclear fusion. This region, destined to become our Sun, was about to undergo an incredible transformation. The proto-Sun, as it was known, would soon ignite, beginning the process of nuclear fusion that powers all stars. This moment marked the birth of our solar system, a new chapter in the story of the universe. Deep within the heart of the collapsing solar nebula, pressure and temperature soared to unimaginable levels. Atoms of hydrogen, squeezed together by the immense gravity, began to fuse. This process, called nuclear fusion, released an incredible amount of energy in the form of light and heat. And with that, our Sun was born. The Sun's ignition was a pivotal moment in the history of our solar system. Its powerful gravity became the anchor, holding the planets in their orbits. Its radiant energy provided the light and warmth that would eventually allow life to flourish on our planet. The Sun, our very own star, was now the master of its domain. But the story doesn't end there. The birth of the Sun had a profound impact on the rest of the solar nebula. Its powerful solar wind, a stream of charged particles, blew away any remaining gas and dust that hadn't already been incorporated into planets. This marked the end of the solar system's formation and the beginning of a new chapter. While the Sun was busy igniting, the rest of the solar nebula was far from quiet. This vast cloud of gas and dust was a bustling nursery of cosmic activity, teeming with the raw materials that would eventually give birth to planets, moons, and other celestial bodies. The clumps of dust and ice that had formed earlier continued to collide and stick together in a process called accretion. This process was slow but relentless, with particles gradually building up over millions of years. Each collision added a bit more mass, and with more mass came a stronger gravitational pull, attracting even more particles. Like cosmic vacuum cleaners, these growing planetesimals swept up more and more material, becoming larger and more massive. As they grew, their gravitational influence increased, allowing them to attract even more debris. This runaway growth led to the formation of protoplanets, the building blocks of the planets we know today. In the inner solar system, closer to the Sun, it was too hot for ices to survive. The intense heat caused any ices to vaporize, leaving behind only the more resilient materials. The planetesimals in this region were primarily composed of rock and metal. These materials could withstand the high temperatures and continued to collide and merge, forming larger and more complex structures. These rocky bodies eventually coalesced to form the inner planets: Mercury, Venus, Earth, and Mars. Over time, these planets developed their own unique characteristics, shaped by their proximity to the Sun and their individual compositions. These planets, with their solid surfaces, are very different from the gas giants that would form farther out. The inner planets are smaller and denser, with surfaces that have been shaped by volcanic activity, tectonic movements, and impacts from other celestial bodies. Farther from the Sun, beyond the frost line, temperatures were cold enough for ices to remain solid. This region of the solar system was a stark contrast to the inner regions, with its frigid temperatures and abundance of icy materials. Planetesimals in this region could grow much larger, accumulating vast amounts of gas and ice. These massive bodies had the potential to become the gas giants, with their thick atmospheres and extensive systems of moons. These gas giants, Jupiter and Saturn, with their swirling atmospheres and numerous moons, are like miniature solar systems themselves. Their immense gravitational fields have shaped the orbits of many smaller bodies, creating complex and dynamic systems. Beyond them, Uranus and Neptune, the ice giants, formed from a mixture of ice, rock, and gas. These distant planets have unique compositions and atmospheres, with features that set them apart from the other giants. Each planet, with its unique composition and history, is a testament to the dynamic processes that shaped our solar system. From the rocky inner planets to the gas and ice giants, the diversity of worlds in our solar system reflects the complex interplay of forces that have been at work for billions of years.